Right. Next question. Again, we have a uniform beam. So the moment I hear the word uniform, the rod or the beam or the rod or the beam that I'm going to draw, it would have all of its mass at the center. So what is its mass? Its mass is 20, so I'm going to times that with g. So you have a force of 20 g's going downwards. The length is 6, so that means I'm going to put 3 meters on my left and 3 meters on my right. This is A, this is B, and I can see there is a support at C. So let me just draw C here. So this is C, and C is 1 meters away from it. So that means this is 1 meters, so this would be 2 meters. Because there is a support, that means there is a reaction force that is going up. The beam rests in equilibrium. That means everything that is all the forces up would be equal to all the forces down, and then the clockwise moments would be equal to the anti-clockwise moments. One support is at C, where AC is 1 meters, and the other end is at B. The beam is modeled as a rod. Right, we want to know, oh, there is a support at B. I kind of missed that one. So yeah, there is a support at B. Now, because if you imagine this to be like a person who is kind of, let's imagine this as a person. His feet is here, head is here. Now, if you imagine this to be a person, he would be experiencing an upward push or an upward force near his, chest and also at his feet. Now, if you imagine, where do you think, imagine you are the person, where do you think you would get the larger amount of force? You would get your larger amount of force on the chest, because that is where, now in this part, you have a large amount of your body weight, whereas on your feet, that is only a relatively less amount of weight that is resting here. So it's common logic to think that the reaction force happening at C would be greater than the reaction force happening at B. So they are not equal, they are different. A common mistake is just to write both of them as R and R. That would mess things up. So they're not equal, they are different. The reason is the larger chunk of the mass of this rod is resting at the support at C. Only a relatively small amount is resting at B. Right, so we've got this much set up. So that's our diagram. We've set up the diagram. We need to find the magnitude. So essentially we are trying to find the what is our C and what is our B. So we've got the diagram. All we have to do now is take the moments. We can choose any 2 points to take the moments, or any point that we like. So before we take the moment part, the first thing I would do, resolving the forces up and down. So all the forces that are acting up would be equal to all the forces that are acting down. So we can say RC plus RB would be equal to 20 G's. So that is the first equation that we have set up. Now, taking moments, you can choose either C, you can choose either B, you can choose A. I'm just going to go with C. The reason why I'm going to go with C is I would then be able to eliminate RC. If you are going with RB, you will be able to eliminate RB and B. If you want to go at A, you will then have your RC and RB. Then the problem is you have to solve it with simultaneous equations. So whichever method you prefer, whichever method you like, you can go with that one. I'm going to go with taking moments about C. So taking moments about C, so that means RC is eliminated because the force is going through my pivot point. Let me just make my pivot point point a bit bigger so that it kind of stands out. So my pivot point is there. So the first force that was actually going to cause a moment is the 20 Gs, and it is going in the clockwise direction. The perpendicular distance between the force and the pivot point is 2. So that means you now have 20 Gs times 2. That is my first force, or that's my first moment. The next force that is causing a moment would be RB, which is going in the anti-clockwise direction, and the perpendicular distance towards the force is, or towards the pivot point, is 5 meters. So that would be RB times 5 meters. So we can now say, solving for RB is equal to 8G. So because RB is equal to 8G, then RC would be equal to 12 Gs. So 8 Gs is 78.4 newtons to 3 significant figures, and then 12 Gs will be 117.6 newtons. So yeah, that's part A. So things that I want you to remember: the reaction forces are not the same. Please do not write them as R and R. That will, kind of complicate things. That will mess things up. Try to highlight your pivot point so that it kind of stands out and you'll be able to figure out what is the distance. The moment you hear the word uniform, the mass, drops down exactly in the middle. And because you know that is the middle, then you have to connect it with the picture, then figure out this is 1, so the remaining of the 3, that is 2. Right, so that is part A. So now for part B, a boy of mass 30 kilograms stands on the beam at the point D, so we don't know what that point is. The beam remains in equilibrium. The magnitude of the magnitude of the reactions at B and C are now equal. So that means RB and RC are now equal. So then I can say both of them are, it's the same. So let's put a boy here, and his mass is 30, so the force he is applying is 30 Gs. We don't know what this entire distance is, so I'm just going to call X. He is X meters away from the middle, so that means he is, so the remaining distance would now be 3 minus X. Right, so we've got that much. What are we doing next? So the beam remains in equilibrium. That means all the forces up are equal to all the forces down. The clockwise moments are equal to the counterclockwise moments. The magnitude are now equal. The boy is more or less. We have to find the distance AD. So what exactly is D? D is the point where the boy is standing. So we have to find what is AD. So AD is essentially, this is 3 meters. So that 3 meters plus my X, that would be AD. So 3 plus X, that would be AD. Right, so first thing that I would do, resolve the forces up and down. So the two forces that are going up, that is R and R. Two forces that are going down, 20G and 30G. So we can now say 2R is 50G, or the reaction force is 25 Gs. So we've actually got what is R. Okay, so let's put that to the side somewhere. So that was 30 G. So the reaction force is 25 G. Okay. Now we have to find the moments. So you would need to take the moment about some point that has the x thing on it. So I'm going to choose this point. Well, you can choose any point you like. I'm just going to choose this point. So I'm going to choose C again as my pivot point because it was already a pivot point. So choosing moments about C, or taking moments about C, the first force that is acting in line with C, you have the 20 G's that is going down, and the distance towards the perpendicular point is times 2. The next force that is going down is, or going in the clockwise direction, is the 30 G's. So that is 30 G. I'm sorry, I forgot the G here. 30 G, and the distance is 2 meters plus the x. That is 2 plus x. And on the other side, or on the going in the opposite direction, is the moment at B. So the reaction force is R, but we know R is 25 G's. And the perpendicular distance, now if you think about it, the entire distance is 6. This is 1. So the remaining distance is 5. Or you can do it the hard way, 2 plus x plus 3 minus x. Eventually it will always add up to 5. So this is times 5. So we now have 40 G's plus 60 G's plus 30 Gx equals 125 G's, or 30 Gx. This will then become 100 G equals 125 G. 30 Gx equals, subtract 100 on both sides, that would become 25 G. Cancel out the G's. X is equal to 25 over 30, which is 5 over 6. So x is 5 over 6. We wanted to find the distance AD. So till here, that is 3. So adding the 5 over 6, that would then become AD is equal to 3, adding the 5 over 6. So 5 over 6 is 0.83. Add 3, so 23 over 6, or we can say 3.83 to 3 significant figures. So AD is equal to 3.83 meters to 3 significant figures, and that is part B. Things to remember from this question. Well, it's essentially the same thing. Yeah, I don't think there's anything new that we did in this question, so that's part